thank you for being here. Thank you for being part of this presentation. But at the same time, I want a little bit of understanding on this side. There are 4 of them that basically graduating this year or graduating next year depends on the next 10 minutes. So I would like for everybody to understand the situation.
Can we put a sign on the door that says abandon hope all you entrepreneurs?
Yeah. Pretty much. Leave all hope on the side. Room number 3, whenever you guys are ready.
Well, thank you, everybody, and good afternoon. It is actually my great pleasure and honor to be able to introduce my project and my group. Our project is the Ultrasonic Small Volume Sensing Workstation. I'm Gregory Boyle. I'm the project team lead. This is Kevin Phillips, our lead programmer. Alexander Tarazov, our team archivist, and Christopher Valler, our chief financial officer. And basically what we had to do was we were teamed up with the Baylor College of Medicine Human Genome Center, and their whole idea was that they have these racks, and these racks have these very small microcentrifuge tubes. And inside of them, they get samples of DNA from all over the world. And these samples of DNA come in different concentrations and different volumes, and all of these samples need to be standardized. And in order to standardize them, they need to measure all these small volumes. In order to measure small volumes, let me show you what it takes for a technician. I myself actually am a biology technician at UT. And in order to find these small volumes, you have to manually pipette, take up a sample. You get a little sample in here, if everyone can see. And then you start to dial this pipette down. And when you dial the pipette down, you wind up getting it. Okay, there's one, and that's 48 microliters. So then I'm going to go to the next tube, pull out the next tube. And again, same process, very similar. We're going to go up with the tube, we get the volume, and then we dial it down. So in the time that it's taken me to take 2, very nervously in front of everyone, my machine over here has actually already gone through 6 samples. So you see how inefficient this was. Furthermore, despite what CSI tells you, DNA is not very stable at room temperature. It can survive, but it's just not a great ideal environment. So all that handling with my finger on the tube, granted the technicians would wear gloves hopefully, it's going to transfer heat to that sample. So they really wanted something that was going to ideally be able to do this. So our proposed solution came in the form of a ultrasonic sensing workstation. And basically what we were looking at was we were looking to achieve 5 to 10 microliter accuracy using an ultrasonic sensor. We wanted something that was able to do that in about 15 minutes, so this way the technician could place it on this workstation, maybe step away for a minute, come back and have those results be able to be exported simply and easily to a CSV file for further analysis. Furthermore, we needed to program a user interface that was very friendly. These are not engineering students, they're not programmers, so they need something that's very simple. When I was in biology, I needed simple. So we designed a GUI that was going to be very simplistic and very user-friendly for these people. Furthermore, we wanted to reduce human error. You saw how much that pipette moved. You saw all that time that it took me to be able to take out that tube. Again, DNA is fairly sensitive. You don't want to be messing with it all this time. So, in order to show you the proof of our concept here using the ultrasonic sensor, I hand off to Alexander, who will further explain the ultrasonic sensor itself.
Thank you. One of the crucial aspects of this project is the accuracy that the workstation is able to provide. This project employs the ultrasonic sensor that is able to provide such accuracy measurements. The ultrasonic sensor features a resolution of 0.056 millimeters or 56 micrometers, which means that the sensor is able to detect a change of distance as small as 56 micrometers. When translated to the volumes inside the test tubes, under ideal conditions, the sensor is able to detect a change of 2 to 4 microliters. However, such ideal conditions can never be achieved because of the high tolerances of the test tube manufacturing, and also because of the nonlinear shape. Through various testing, it was verified that the sensor is able to consistently provide 5 to 10 microliter accuracy, which is a pretty good result because the manual pipettes itself have tolerance of 5 microliters, and that's without even considering the human error that always arises with the manual pipetting. The way we approach this is we did the regression analysis data method on those test tubes, and we took multiple samples of volumes, as you can see here, from 0 to 200 microliters in 2 microliter increments, and we measured the corresponding distance between the sensor's transducer and the liquid meniscus in the test tube. and we fitted the straight curved line, well, I mean, it's actually not linear, and we fit the cubic polynomial formula to it, and based on that formula, we did various rounds of testing through which we were able to verify that the sensor provides 5 to 10 microliters of accuracy. And so the next important part of the project was creating a whole system for automation, or basically creating a system that automates the whole scanning process. And for that, I'd like to hand this off to Christopher Veller, who will talk about the main system layout and its components.
Thank you. Our system layout is more of a master-slave protocol, meaning our Raspberry Pi will be the one controlling everything, all the peripherals that you see below it. We have the GUI, which will be the monitor here. You have the motor and the driver motors, which will be inside this compartment. You have the ADC, which will also be in here, and you have the sensor that is mounted right here. As you can see, we have the test tube platform that moves in the y-axis. You actually put the test tubes here, as you're watching, at a certain distance for the sensor that is mounted here. For further explanation, on the XY motor, I'll go ahead and give it to Greg.
Okay, so we had our initial, task was in order to figure out how we were going to measure these small volumes. Microliter is a very, very small volume. 5 microliters is a small volume. So we were able to use this ultrasonic sensor with a very high resolution to tell that difference of distance and translate that to a volume. But further, we wanted to automate this whole process. As you can see, we're moving along the X and Y of this rack. This rack is extremely standardized to Baylor College of Medicine. These tubes, the system has been basically built around these systems. Or rather, they buy centrifuges and sequencing machines that use these tubes. So we needed to utilize this rack. And so what we decided was we were going to move along the X and Y plane, and we were going to fix the X coordinate because, as you can see, it's the longest distance. This was going to be Y, this was our X. So what we came up with was a system where the X platform is actually mounted to the workstation, and the Y drive is mounted to that X platform. Therefore, we can achieve X direction and Y direction automatically with 2 different motor systems. We used stepper motors in this case with 1.8 degree angle of step. They can basically do 200 steps per revolution. But then we integrated this with some real nice high accuracy motor drivers. These are TV6600 microstep drivers, and they're able to achieve, instead of doing 200 steps per revolution, now they're doing 3,200 steps per revolution. This is, millimeter accuracy. We have 8.95 millimeters between the test tubes, and so we needed to truly be able to get that sensor tip to the very, very center of each of these tubes. That was extremely important because our regression data is all based on that distance, and that distance needs to be maintained throughout all 96 wells. Furthermore, we needed a power supply that was able to power these 2 fairly high, they're running about 1.8 amps stepper motors, so we wanted a power supply that actually kind of overpowered this. We didn't want something that was going to be powering the stepper motors and creating more heat within this electronic compartment. So we have a 24 volt, 14 amp power supply. Kind of overkill, but at least it doesn't get super, super hot. It actually stays about 90 degrees within the compartment. For the sensor, however, we needed to really, really clean out the 24 volts. And so we actually chose a separate power supply with a very clean output that does not oscillate or vary when powering the motors. And so this power supply is dedicated solely to the sensor. It runs through a MOSFET, which basically just acts as a gate, and when we energize, acts as a switch. So when we energize the gate of the MOSFET, we actually turn the sensor low. It's active low, and then it takes a reading, which then goes to our analog to digital converter, which you can see here under this box. It's very delicate machinery or electronics, so we wanted to make sure that that stayed, well protected. It's a 0 to 10 volt, which corresponds with our sensor output, 0 to 10 volts, as well as a 16-bit resolution. We really wanted to achieve all those resolution that we could from this ultrasonic sensor, so that's why we went with a little bit of overkill. Truly, we needed 13 bits, but we decided to go with 16, just for fun. Further, this is all driven by the Raspberry Pi through I2C communication protocols. So this way, the Raspberry Pi is able to get values from the sensor, is able to control the motors, is able to control store these values in an array, and then export later, which actually leads into our graphical user interface, the GUI, which was programmed and will be explained by Kevin Phillips.
Okay, thank you very much, Greg. So, previously described, we got through all of these mechanical components, but the one part that really glues all of us together and acts as the master control system for this whole entire project is this GUI. Now, it was programmed using PyQt, which is the Python version of the Qt GUI building API framework, which is in C++. But everything going on behind here, there are several different systems that are happening right now. Right now there is a X and Y coordinate system that is going on in the background, and each of these, the GUI is taking information from where it is and it's relaying things between the GUI, the sensors, and the XY stepper motors. So the unload button, what it does is the sensor is fixed, so we need to move the rack out of the way for a stable load. We don't want anyone touching that sensor whatsoever. So the unload button just unloads to a safe location where you can safely put the rack inside the platform. And then once that is loaded, then you press the load button and it goes back to the origin. And then from there on, you can initiate a scan cycle. So another thing that's going on behind the scenes is processor threading. This GUI needs to be able to relay information back to the user at the same time as it's scanning. So to implement that, we used processor threading so that whenever this was taking control of the motors, it wouldn't freeze up the GUI. And information can then be relayed back to the user dynamically and inform them of the progress as it's going along. Okay, so at the end of this scan cycle, which is, I believe is just happening right now, there is an export function. And this export function outputs a CSV file full of the volumes that it just scanned. So this is done for easy access. There is the USB port right there. A technician can easily put their USB drive in there. And this file outputs all of the volumes that it just measured along with a date and time stamp for easy use. And with that, I will be turning the presentation back to Greg. Here's Chris.
To me, Christopher, sorry. For future possibilities of our workstation, we see that we can reduce the platform to smaller, so it won't take too much space. By doing that, we will be using the Bluetooth capability of the Raspberry Pi, meaning the technician or the doctor or whomever is overseeing this can actually look through the tablet instead of having a monitor and a keyboard. We'll be enhancing the GUI by adding more features into the GUI. We will be also adding additional automated add-ons as far as Greg had, I'm sorry, I'm not very good at speaking. As far as automated diluting processes, we can add these onto it and it'll actually just lower the rack into the platform and actually do the whole thing without any human intervention. For marketing, at the moment, we're doing the medical sector. However, as the future develops and as Congress changes laws and so forth, we will see, we're actually maybe most likely modify the whole workstation for aerospace and oil industries, and also for government entities as far as the Justice Department. As for the cost of our whole platform, I will go ahead and direct that to Alexander.
The project was sponsored by the Baylor College of Medicine, was an estimated cost of under $1,500, including the manufacturing cost of the platform. The platform was manufactured by the University of Texas Tyler CNC machine and was given to our group for free. However, including the cost of the CNC technology, comes out to about $1,500. And acknowledgements, our team would like to acknowledge and kindly express thank you to Dr. Robert Charles Glenn, the research scientist of the robotics department at the Human Genome Sequencing Center of the Baylor College of Medicine, and Dr. Melvin Robinson, the program director of the Houston Engineering Center at the University of Texas at Tyler. With that in mind, we'd like to conclude our presentation And if you have any questions, please feel free to ask me about right now. Thank you for your attention. Any questions?
Okay, first right off the bat, well, first of all, technically, this is one of the most impressive things I've seen. It's very shiny. I like that. It's
Well, that's
the most
aluminum?
impressive looking. Well, not just
The
that.
aluminum, okay.
It looks
We
cool.
both.
I gotta give you that. But right off the bat, one thing I didn't quite understand was, again, maybe it's obvious for someone with a biology background, but I don't think you ever truly explained to me why I would want to precisely measure. Okay, I understand why I would want to know, have a certain volume in the pipette, but I would assume I put it there in the first place.
Absolutely.
So why would I want to know that?
Oh, that's a great question. So I you know, as a biologist, samples are coming in from around the world. Basically, the Human Genome Center at Baylor College of Medicine is a huge center where they're sequencing our genome. Samples come in from all over. Samples come in at different concentrations, different volumes. They're also a staff of probably about 300 different technicians. A lot of their process and processing, sequencing, and all this is automated as well. And so samples can get kind of mixed, matched, and whatnot, and you need to know those volumes. The real reason you need to know volumes is because based on the concentration in the volume, you dilute. And so sequencing, PCR, so PCR is a polymerase chain reaction. That's where we amplify parts of the DNA. Where we amplify the parts of the DNA requires enzymes. Enzymes require specific concentrations based on the template DNA. So in order to fully maximize the efficiency of your reactions, you need to know what your concentrations are or dilute to a standard. So the real reason you would want to do this, these are 2 racks. They have hundreds of thousands of racks. Because at one point we had a problem with these tubes. The high manufacturing tolerances, like Alexander had talked about, led to a very, very difficult process of finding a formula that would give us the volumes of all these different tubes. So what we wound up doing was doing the regression. Because Baylor College of Medicine, when we said, you know, maybe you should change your tubes, they said, well, maybe we should change our group. So we kind of were like, okay, well, we'll figure out how to deal with what we're dealing with. So in their realm, you know, these tubes are king. And so we needed to know like 100% what these tubes were capable of. And again, the whole reason is because they're working on a huge scale. Their sequencing machines are multi-million-dollar next-gen sequencers, and they're very, very specific reaction values. So the reason you want to know all the values of volumes within that rack is because those volumes need to be standardized. And to have a technician go through 96 tubes to standardize 96 tubes takes forever. And it's just not a very efficient process. So that's why this would be something that would be very helpful. Also, as well as what Christopher said in the automation process in future add-ons, if you had a station that automated your volume sensing, you could also have an automated dilution station. And basically the values from here that Kevin's now showing you, exported here into a CSV file, we can further take these values. These are in CSV float values, which is just a simple program. But if we took that array and put it into another program that was able to take that array and then put it into a diluter, the robotic diluter would know what volume to put into each one of the tubes in those locations because it's all based on this coordinate system. So then further, the system could further automate the whole process of standardizing samples. So, great question, thank you. And let's see.
What is your quality indicator to really check on this output versus what is the input you have here? Do you have some kind of a matrix to show, whatever you do here really would meeting with your requirement there?
Yes, absolutely. Yes, sir. So, so a lot of our standardizing and ensuring quality comes from, we used an analytical balance first of all. So we made sure that we had very pure water. We went to my lab a bunch of weekends and we measured a bunch of times the actual volume of water based on analytical balance. So instead of using the pipettes, which Alexander had mentioned, do have tolerances of what's respectable in their plus and minus. So we would weigh the water to get the true volume, and then we would translate that to distance. And basically what we did was we did that over and over and over and over and over again, and that's why we fit to the linear regression here. And basically what we were doing, so another big thing is, this kind of biology, but we usually look in the realm of 30 to 70 microliters. That's what you standardly elute DNA into, and so that's like the realm that Dr. Glenn was really concerned about. So that's why we actually went with a cubic that was perfect fit for this little area. And then what we did was we consistently would fill up the tubes with various volumes from the pipette. We would pipette it into the system, and then we would measure them. And actually what we found out was, and maybe it's just because in my lab we haven't calibrated our pipettes in a while, but the system that we developed was actually usually closer to the actual volume than the pipette was measuring. So I would measure 45 and I would get 46 in the weight.
Really, my point is, for all the engineering projects, you should have an engineering specification. I'm asking for the engineering specification, okay? So that's where leading to the quality check, right? So otherwise, I believe what you said, I believe what you guys did a wonderful job. I'm really impressed. This is a wonderful project. But again, any engineering project should have specification first before you develop the process, procedure, whatever other things.
Yes, sir.
So that's just my suggestion to you.
Okay, yeah, so our main goal was to make it to 5 microliters, to have 5 microliter accuracy. That was
that's the goal, so you
that was
can
our
check
goal,
it.
and we were able to achieve
Thank
it.
you.
Yes.
Okay, and mine's related to that. You ran a cubic spline interpolation. I was wondering if you did a test statistic off of that to see your accuracy, so that you could get like chi-square distribution to say, it's a 95.
We did apply some further analysis. We have an R-squared value. The R-squares, when we did further analysis, depending on the actual volumes, we found that this was the best fit in this realm. So in this realm right here is what we were really concerned with. And that's why we went from 0 to 200 to see if it achieved a better result. And whenever we would fit to a higher degree, it actually wound up kind of scrambling back that area of interest. And because we were so focused on that area of interest, that's why we ultimately went with this area. But more statistical analysis would absolutely be crucial. Thank you.
Same question.
So, yeah, I have a question. So, is this machine designed to run 24/7? Or is this machine designed to run 24/7 and you're getting towards it?
Yes, absolutely.
And so, like, suppose if it's in a process and there is a glitch in the system and it stops, suppose in one position while it's filling one of the wires, and you restart the system, does it memorize the position whether it's on the array, or does it go back to the first position?
So that's a great question, and actually, I believe Kevin Phillips can answer that, whether or not the system knows what position it is in.
So inside the Python programming, there is Qt uses a system called signals and slots. So what that means is one part of the program can send a signal to another part of the program, and the way I use that is there are 3 objects in this program. There is a loading object, which controls the loading and unloading, and there is a scan object. So what happens to keep track of where this thing is these scan and load objects, once they're done with their functions, they send their coordinates back to the main GUI. So what happens is, whenever you do a scan cycle or something, the first thing it does is it pulls the coordinates from the main GUI object. So since everything has to send it to the main GUI at the end of its cycle, and everything has to pull from the main GUI, it always is tracking its position, no matter what part of the scan cycle that it is. Does that answer your question?
Yeah, some part. But what happens that if it has not finished filling that wire, it's in the process?
Oh, if it's in the process. So that is something that would be covered by our future implementation. So my personal plan for it was, what you're talking about is an abort cycle, right? An abort. So what would end up happening is, for an abort, I would also make another signal, and this signal would trigger an abort exit function. So in Python, there are some things called exceptions. So what this would do is it would raise an exception, it would finish the scan that is that it's going on, and then as soon as it finishes that one, it would send the coordinates where it is back to the main GUI, so that whenever, let's say you abort it right now, what would happen is it would stop, it would finish its scan, first of all, it would stop, and then from there you can press load, and it goes back to the origin, and you can press unload, and you can just start all over again. That would be a future implementation, but I have a very clear idea of how to do that.
Okay, this is in line with the interpolation, all this kind of stuff. Can you go back to your slide that showed your Excel output or your CSV output? Okay, So that's a very impressive accuracy. That looks like a, what is that, a billionth of a microliter?
Yes.
So that thing measures volume to a billionth of a microliter.
The output of the ADC is to the billionth of a microliter. Whether or not it would actually, if you put in a billionth of a microliter, would it be able to accurately measure that? No. Because what we're ultimately looking at. So what we would do is we would clean this to and float back to 2 decimal places.
Okay, so that's what I want to see, because this is a piece of scientific equipment.
Absolutely.
And so, now I don't know much about that ultrasonic sensor, but there's no way you have readings accurate to a billionth of a microliter.
Understand.
So that is
so again, that's going to be
incredible numbers.
So we're, the other thing is the CSV file needs to be cleaned up further. We want to implement a CSV file that has multiple sheets, that has multiple layouts as well.
So I want you to analyze your whole process statistically, figure out how many significant figures you have, and report just that.
Okay.
That's what I'd like to see.
Absolutely.
Just in regards to the XY plane, did you have any issues like with calibration? Like if you're using this system over and over and over again, do you have any issues where when you're trying to go to a certain test tube location where it would maybe think it's off by a tube or something? And if so, how did you handle, like re-zeroing process?
So again, using the stepper motors, part of the user manual will be actually further calibration. So one of the great things is you can turn it off and then you can actually dial the stepper motors to the center location of the origin. And basically, while the stepper motor is going, we have not seen the glitch where it would overstep that boundary. We set up that boundary. We use the micro stepper driver of a 32th of a step in order to achieve that accuracy. If it were to overstep at all, it might be within a few micrometers. So again, a lot of what we did internally with the motor drivers and the stepper motors was overkill in order to achieve and maintain that accuracy and precision.
I'd like to add one thing to that point. So that the accuracy of overstepping actually boils back to our decision to use stepper motors. So stepper motors are very, very, very accurate motors, and that's the reason we chose to use them is because they're so accurate that they are very reliable in open loop systems. So to make it a closed loop system, other motors use encoders to count the number of steps that they've gone. But as far as that goes, that would increase the code, and it will increase the complexity of our project. And one of our main goals of this is for anyone to be able to calibrate this and get this done. Greg mentioned that all you have to do to calibrate it is get your fingers and center in the first tube. So if we have a technician dealing with the feedback system that controls how these motors keep track of themselves, it introduces a lot of complications, and it really reduces the modularity of how we can replace broken parts, how we can calibrate on the fly.
Yeah, as a person in the lab, when that happens, we usually have to box it up and send it back, and thousands of dollars are spent getting the bio-rad to recalibrate our plate readers.
So you mentioned that the long-term goal is to integrate this into a process. So you'd have some sort of robotic arm conveyor belt system, putting one rack, measuring the volumes, putting it over here, moving through hundreds of these trays ideally, right?
Yes.
So you would ideally have this 24/7 in operation. So in that kind of load case, one thing you brought up at the very beginning was heat. How much heat is that gonna heat up if that thing is running 24/7? Is that gonna be a problem at all?
So as of now,
and
we've
all that?
run it for several hours,
Okay.
and it does not get hot. Furthermore, if it was in the process of doing dilution within DNA, most likely, and for our recommendations, would be to put it in a 4-degree room. So that this way, the room itself maintains the environment, and as far as the motors and the box are concerned, they could even be further externalized. And then the room would maintain that temperature. The stepper motors would produce a fairly negligible amount of heat.
So the whole room would be at 4 degrees Celsius?
4 degrees, absolutely.
Okay. And so that would be maybe, oh, I guess that makes sense. So maybe somebody wouldn't have to be in there all the
No,
time.
absolutely.
But it's,
Yeah, so a lot of processes, we do have rooms that are temperature controlled. And we have a room that's a 4-degree room, and we do protein. We have another room that does, other types of processes. And this type of machine and that kind of system that does all these serial dilutions running 24/7, I would absolutely recommend 4-degree.
And how susceptible is this to vibration? Like how, because if you're one of those big processes, lots of belts and arms moving things around, how susceptible is this to vibration?
So as of right now, we have locks on all of our positions for the sensor, the rack. At that point, I would recommend having vibration dampening legs for the actual table. In this case, we didn't really feel the necessity to have the vibration reducing, but you could absolutely have vibration reducing.
So I think Professor Larson's question links up to my comment earlier. We need you to have a specification for the shock, vibration, temperature range, so you can be assured when you design something, it's repeatable. So within that calibration, the range, it will be performed. Okay? I think that's a very important question. Link up to the specification again.
I'd like to have one question. Mostly in regards to what he was mentioning, there has to be a system that just by having an auxiliary tracker that will comply that if I'm in position 3-3, that there will be this auxiliary tracker that will tell me, yes, you are in 3-3. Okay? And in order to maintain that, that will be basically, yes, we can trust in the stepper model, we can trust in the things. But in the same way that we trust in our engine, but we have a sensor that tells you we have a defect in here. So before you damage more samples, that the actual instrument can tell you, stop, there's something in here that is not actually matching. So just as a backup.
Yes, we absolutely want fail-safes. So further implementation would have other fail-safes. We would have positional sensors here and here in order to cut off the entire program, kill switches basically. We could have temperature kill switches to where even on the rack itself, the way that we machined it with the thickness, we could actually put inside of there little thermal sensors that say, hey, your temperature is reaching a critical limit, cut off the system, warn the technician. If we have Bluetooth capability with our Raspberry Pi, it also has Wi-Fi capabilities. So you can actually relay into this using an SSH client and be able to get signals from that wherever you are. And that could tell any technician that may have placed a plate on there and walked away, hey, your sample's now reaching a critical temperature. Hey, the stepper motor went crazy and it threw your plate on the ground. There's vibration, the position of this is now off, and so we would be able to maintain that. We could even further put an accelerometer on the actual sensor itself, and it would be able to tell us if that moved in an XY coordinate plane. And so, I mean, absolutely, there's definite need for further implementation of certain standards to maintain and make sure that we ensure the validity and safety of the samples.
One thing I'd like to add on to that is that the reason I think I want to emphasize about our project is that it is very expandable. And that's largely in part to QT, which is that signals and slots method that I talked about earlier. So these signals and slots, depending on how many sensors we hook up to this, we can have all of these sensors sending signals back to what needs to be handled. So as long as we have space on the board, we can hook as many sensors, we can set off as many warnings as we want, and we can handle that because of how dynamic the signals and slots method is. It can send any warning to anywhere.
As a civil engineer, I do have to ask, can I get the output in English units? Put a button on the GUI to get English
Absolutely.
units?
You know,
Okay.
we could even have it to where you have a whole thing that says, America standards over
Oh,
here.
perfect.
And this way you can have all those. I don't know if you ever use like gallons and whatnot to do microliters. I'm sure that would be a very
Picogallons.
Picogallons, exactly. There we go. So absolutely, no, we would make that happen for you.
So we thought of that in advance, actually. That's why it's in column format, because you can just click, drag this column, and apply any formula you want.
Oh, okay.
Any further question? Thank you.